you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hi, this is Mr. T with a tutorial on exponential functions. I'll be doing this tutorial in 4 parts, and this is the first part. We're going to get an introduction to exponential functions and understand how they behave by looking at their graphs. So let's first look at an exponential function, y equals 2 to the x. Now, as we're getting familiar with a function, one way to get a picture or a graph of a function is to make a table of values. So I've picked some values of x here and our function here, so we need to calculate the y values. Let's start here. So y would be 2 to the 0 power, which we know from our exponent properties is 1. Here we have 2 to the first power, which would be 2. And 2 to the third power here is 8. So you can see as we're increasing our x values, we will keep, every time x goes up 1 with this function, our y value will be doubling. So it'll be increasing quite rapidly. Let's look at what happens when we go to the negative. So 2 to the negative 1. Remember from our exponent properties, a negative exponent can be converted to a positive exponent by taking the reciprocal. So we have 1/2 or 0.5 here. And if we do -3, that's going to be 1/8, which is approximately 0.125. So you can see with the negative exponents, our numerator will stay 1 and our denominator will be getting bigger and bigger. If you take the number 1 and divide by bigger and bigger numbers, we're going to be approaching 0. So as we head out this direction, we're going to be getting closer and closer to 0. That's called a horizontal asymptote. And as we go this direction, we get large very quickly. So if we plot our points, so we're at 1 at x equals 0. At x equals 1, we were at 2. And at x equals 3, we were up at 8. And at -1, we were 0.5. And out here at -3, we were 0.125. And again, it's not going to ever equal exactly 0, but it's going to get closer and closer. So if we connect our pattern here, we can see that the graph, now that wasn't a very good graph. I'm not really good with this pad here, but this is going to keep going up, not straight up. It's going to keep going out. Let me see if I can do that better here. It's going to keep heading to the right, but it's going to keep going up very fast. So it's kind of like some people call this a knee curve. So around this area, it starts going up very rapidly. So, and then over here again, it's getting closer and closer to 0, but never touching 0. So we're going to be using this model. In our last example, b was 2, that's the thing with the exponent, and a in the last model was 1. Now this will be our general model, and we want to look at what happens as we change various values. So let's stick with our base function of y equals 2 to the x, so that would be 1 times 2 to the x. And I'm going to make it quicker here, let's use a graphing utility to look at the graph. So let me put in here 2 to the x power, and we'll graph that and get our baseline here. So you can see that's the same graph we just did. So let's look what happens if we increase a. So let's say what if a is 3. So we're going to have 3 times 2 to the x. So let me put that into y2 so that we can have a comparison. So let's look here at 3 times 2 to the x power. Whoops, I forgot the exponent. And let's graph. So that was the first one. So now you can see we're going up a little more steeply, and our y-intercept went from 1 to 3. Let's look at what happens if we make a equals 5. I'll add a third one here. It's going to get a little bit busy. So here we've got 5 times 2 raised to the x power. So you can see it's getting even more steeply, and if we zoom in now, our y-intercept is 5. And let's look at what if a is a fraction. So let's look at one last example here. So let me go back here. Let's get rid of a couple of these so that we can see what happens. And let's put in now 1/2, which is 0.5 times 2 to the x. And we'll see it's not going to go up quite so steeply. And if we zoomed in, we would see that our y-intercept is at 0.5. So when a couple things. A gives us our y-intercept, which is our initial value, meaning our value when x equals 0. That's really the most important part of A. And then it can also affect the steepness. So when A is greater than 1, it gets steeper. And if A is a fraction, say between 0 and 1, it is less steep. Now from our, let's look at one last thing. Let's look at what happens if A is negative from our discussion of translating functions when we did quadratics. If you remember the A in quadratics, if it was negative, it flipped the curve. So let's look at what happens here if we replace this with, say, negative. We'll put -1 in for A. So let's say -1 times 2 to the x power. And let's graph again. So here is going to be our base function here, 2 to the x. And as we can see, it flipped the function. So if A is negative, we're going to flip the curve. So again, a key item here is it's our initial value when x equals 0. Let's look at the effect of b. So in all of our examples so far, we had b is 2. So let's look at a couple examples. So let's start out by making b bigger. So let's look at y equals 2 to the x, say 3 to the x. Whoops, that's supposed to be a y. And we'll do y equals 5 to the x. So let's look at those. So we've got our 2 to the x. Let's make this 3 to the x. And let's do 5 to the x. And let's graph. So here coming first is 2 to the x. Comes 3 to the x. And 5 to the x. So you can see it gets, they all have the same y-intercept. They all asymptote out here at 0, but they rise after we get bigger than 1, they rise more steeply. And that's because what we are doing here is every time we increase x, we're multiplying our result by this b. So if we're multiplying by a bigger number, it's going to grow more rapidly. So when b is greater than 1, we are growing and growing more rapidly. Now let's look at what happens if we look at a fraction for b. So let's say, what if we had y equals 1/2 to the x? So let me enter our functions. Let's clear these out. And let's put in, say, 0.5 to the x. Now this looks weird because it looks like the same shape as y equals 2 to the x, but it's going backwards. It's going bigger over here. Now this would make sense because if we move that 2 to the 1, that would be y equals 2 to the negative 1 to the x using our exponent properties, which would be y equals 2 to the negative x. So when when b is a fraction, instead of going from, if we go left to right from 0 and then rising rapidly here, we start out really big when x is a negative number, and then we're flattening out. So when b is less than 1 but bigger than 0, we have what's called exponential decay. Our function value is getting reduced. And just like before, if we make this number smaller, so let's just do one more. Let's say, what if it had been about 1/4, which would be 0.25. We can see as before it decreases more rapidly. Now b and these exponential functions will never be a negative number. A negative number raised to a power behaves very erratically. So on our exponential models, b will always be a positive number. A could be positive or negative. Remember, when a is negative, it flips the curve around the x-axis.